Hello, everyone. So today we're going to be picking up where we left off with kinetic gases. So we previously determined an equation for the velocity of a gas moving through space. But today we're going to run into a slight issue. That velocity is mostly useful if I'm, say, looking at how the gas interacts with, say, a wall of a container or something that's stationary. So this can be useful if I'm trying to, say, determine the pressure of a gas, but it's slightly more complex if I'm trying to look at how the gases interact with themselves. So for this, what I really want to care about is relative velocity. So this is going to give me a lot more information about how gases interact with each other. So this is going to give me a lot of the collisions that can help do things like start driving chemistry, because it turns out for a lot of chemical reactions to occur, it turns out that two gas molecules need to hit each other. So this might be something that's a little bit more relevant for our sort of chemical level understanding. So it turns out that if we're trying to determine relative velocity, determining the equations can actually be a little bit tricky, but we can kind of uh, simplify the system by breaking it into three idealized cases. So we can imagine if I've got two gas molecules, the extreme cases, the two gas molecules are moving in the same direction. So then it's simply going to be the speed of this molecule minus the speed of this molecule. So this means that in net, or on average, my average relative velocity is going to be zero, as they're just going to keep missing each other. Alternatively, we can have a head-on collision. Okay, that's not exactly going to be that common either, but a relatively simple case is it's going to be the two velocities added to each other. So that's pretty nice. But we have all the other cases where they're going to hit at some oblique angle. And so the model or average example of this would be two gas molecules hitting each other at a right angle. So what we can do is figure out what's going to be the energy of collision if these two interact. And so we can essentially use as a little bit of vector math, or for a more simple idea, just simple geometry. So I've got these two angles for the velocities of the component vectors, and then the net velocity, or the relative velocity, is simply going to be these two added together. So this gives me classic Pythagorean theorem. So v squared plus v squared equals the net value, which is going to be the square root of 2 of these two added together. So this means that if I'm looking at molecular collisions, they're going to tend to have a relative velocity of square root of 2 times the velocity, times my starting velocity. So essentially you can think of, I have the velocity of my starting molecule plus a little bit of extra from the second molecule hitting it. So hopefully this kind of makes sense. So in a net sort of perspective, or an average sense, this is going to be kind of uh, the relative energy or velocity that these two molecules are going to interact. Now, what I really need to do is try and use this relative velocity to give me some sort of information about how common the collisions themselves are. And in order to do this, one of the ways we can do is just simply look at, if I have a gas molecule and it's traveling through space, kind of what's its area that it's carving out. So if I've got this molecule, it's traveling forward, any other gas molecule that gets within a certain distance is going to end up colliding with this gas molecule. And you can imagine that if I'm looking at two identical gas molecules, this is going to be essentially the same as this radius plus the radius of the second gas molecule, or kind of an effective diameter. Now, because the diameters of interactions or interaction distances can be a little bit of tricky, what we often end up doing is determining this d parameter a little bit more empirically, but it will give us an area of interaction that's going to be related to uh, 2 pi r, 4 pi r squared, or pi times the diameter squared. So again, classic sort of um, geometric constraints. So this actually can be quite useful. So then, however, it's worth noting that this cross-sectional area is often determined a little bit more kind of empirically. However, knowing the area of interaction alone isn't sufficient. I also need to know the total volume of interaction. So essentially, how far will this gas molecule travel, carving out this cross section through space? So this is essentially going to be my area times this distance, which is going to be related to the relative velocity times the time interval I'm looking at. So in a certain time of say 1 second, I'll carve out a volume of the relative velocity times this cross section. So this is actually a fairly useful idea. However, what I'm usually really care about is how common these collisions can occur. So if I'm trying to determine the number of collisions, what I'm going to want to do is make use of this volume times the molecular density. So my number of collisions is going to be related to what volume of space is my gas carving out, and essentially how many molecules are in that volume. So what we can do is express this as, again, my volume expression times the number of molecules divided by the volume of interest. So what we can then do is relate this number of molecules per volume with the ideal gas law. So it'll be the same thing as P over KT. So now I can make use of, I can go ahead and collapse this equation down into a single form. So my number of collisions is going to depend upon essentially the size of my molecule, how fast it's moving, the pressure, which is going to be another measure of the density of the system, the time I'm looking at, a constant, and essentially temperature, which is going to be also related to my velocity and give me a certain measure of the energy of my gas molecules. So what we can then do is turn this into a frequency of collisions. So I don't generally care about how many collisions occur. What I really care about is the number of collisions that occur per unit time, say per second, per minute, that sort of thing. So all we need to do there is take my number of collisions and divide it by the time interval of interest. And so then what we get is really just our number of collisions equation, where we just factored out the time system, the time component. And so this gives us a general idea of how many collisions are going to be happening essentially per second. So this is a very kind of useful metric. So this is going to be a quite convenient way to more or less look at how much interaction I have in between my molecules. However, turns out that sometimes what I might want to know is how far my molecules are traveling between collisions, because this is going to give me a lot of information about how gas travels, which you can imagine in current environment can be quite important, as I might be looking at, say, how far a water droplet that I just sneezed out might travel before it hits something. You know, that might be a useful thing to know. So what we can do is express this as the mean free path. So essentially, this is how far will a gas molecule travel before it hits something. And this can more or less be expressed as as a ratio of the speed of the molecule per how many collisions happen per second. So if I know how fast it travels, and I know how far a molecule travels per second, and I know how many collisions occur per second, this will essentially give me how far will it travel before that first collision on, again, an average sort of tendency. However, we want to try and essentially re-express this in terms of some more measurable quantity. So let's go ahead and insert our equations for relative velocity and collision frequency. So our relative velocity we'll leave as is, put in our number of collisions, and what we're going to see is relative velocity cancels out, and what we have is the distance that a molecule travels before it hits something is really just going to be related to the temperature, the size of the molecule, and pressure, which is again another measure of concentration of our gas. So this actually has some rather cool implications. So in general, what this is going to mean is that if a molecule has a higher mean free path, so this value is larger, this means it's going to have a higher rate of effusion. So this is essentially if I release a gas molecule into an empty room, how far will it travel? Or diffusion, which is essentially the more typical, how much is a gas molecule going to move in a matrix of air? And a way to kind of think about this is that the longer my mean free path is, the longer I can travel in a straight line before I hit a collision, bounce off in a different direction, have another collision. And what this really does is it helps us build up a model of how molecules move through a matrix. And mean free path is a very important feature in this. The longer the mean free path, the more time between collisions, a little bit more directional movement we end up having. But it's entirely possible to use some of the information we've already built up and some of the knowledge we're going to build up throughout the rest of the semester to build up what's called Brownian motion. And this is essentially the idea of how molecules move and interact with their surroundings to give us essentially this idea of diffusional movement. But again, just specifically looking at the mean free path, what we find is that this molecule can travel further if we increase the energy, because if I increase temperature, I'm increasing the energy of the molecule, increasing its velocity. If I reduce its concentration, so if I have a smaller pressure, less interactions, more straight line movement, or just have a smaller gas, which will also reduce the number of collisions. Conversely, if I want to increase the mean free path, I'm going to use a slow moving, low temperature, large gas in a highly concentrated system. So this can actually be a very useful way of looking at how molecules move in a kind of a more rich environment. So this kind of brings us to the end of rather simple gas systems, and we're going to try and bring back what sort of things the ideal gas laws and equations, including our kinetic gas we've worked with, miss in kind of a larger system. Till then, take care.